Okay, today we'll be talking about the vector war. Here we have three dapper gentlemen that we'll be getting into later. On the left side, we have William Rowan Hamilton. In the middle, we have James Clerk Maxwell. And on the right side, we have Oliver Heaviside.
Sir William Hamilton lived from 1805 until 1865. He was a mathematician and astronomer born in 1805 in Dublin, Ireland. He was sent to be raised by his uncle, who noticed Hamilton's young brilliance and gave Hamilton a copy of Euclid's Elements. Hamilton enrolled in Trinity College, Ireland, in 1823, where he excelled in mathematics. In 1827, he published his first paper on optics, was appointed professor of astronomy at Trinity, and appointed Royal Astronomer of Ireland, all while an undergraduate. In 1835, Hamilton was knighted in a meeting with the British Association for the Advancement of Science. Hamilton was president of the Royal Irish Academy from 1837 until 1846. In 1833, Hamilton became interested in complex numbers and the idea of extending them into three-dimensional space. The origin of quaternions. In the 1830s, Hamilton was searching for a way to extend imaginary numbers into 3D. They worked well in 2D, but could not naturally represent rotations in three-dimensional space. After 10 years of struggle, he realized that a consistent multiplication system required four components, leading to the invention of the quaternion, a mathematical extension of the vector system. He had his eureka moment on October 16, 1843, while walking on the Broom Bridge in Ireland with his wife. He suddenly had a revelation, discovering the key to expanding complex numbers into higher dimensions. He carved the following formula into the bridge. I squared equals j squared equals k squared equals I times j times k equals -1. While the original carving hasn't survived through time, there is a plaque in honor of where it once was in Hamilton's honor. Fun fact, every year on October 16th, mathematicians meet up and walk along the Royal Canal to the bridge. So, what does this formula mean? It defines the fundamental algebra behind quaternions. Similar to complex numbers, where I squared equals -1, Hamilton introduced two additional imaginary units, j and k, which also squared to -1. What makes quaternions unique is how these units interact through the identity I times j times k equals -1. This relationship leads to non-commutative multiplication, meaning that the order of multiplication affects the result. For example, I times j does not equal j times I, which is a major departure from the regular number system and a key feature that allows quaternions to model three-dimensional rotations accurately. A quaternion is composed of one real component, w, and three imaginary components, I, j, and k, where I, j, and k follow the relation I squared equals j squared equals k squared equals I times j times k equals -1, as we've seen previously. Quaternions can be written in multiple ways, but will always have four components. Q equals the real component w, comma, I, j, and k, or Q equals W, comma, V, where V equals the imaginary components I, J, and K. Quaternions can be visualized as a rotation W about a unit vector R. This is made more clear by rewriting the quaternion as Q equals cosine theta, comma, R sine theta, where R equals R sub x, R sub y, and R sub z. The angle theta can be determined from W. Notice that this is a unit quaternion, w squared plus I squared plus j squared plus k squared, and if you take the square root of that, that equals 1. If you think this is unnecessarily confusing, and that it would be much easier to just use the vector r itself without any of the other funny business, then you're in good company. Oliver Heaviside thought the same thing and worked to eliminate quaternions from mathematics. Operation derivations. Now that we have the rules that define this new number system, we need to rederive the basic mathematical operations to see how they change. For these derivations, we will be using two quaternions, q equals w comma v equals w plus xi plus yj plus zk, and q prime equals w prime comma v prime equals w prime plus I prime times I plus y prime times j plus z prime times k. Addition and subtraction works as one would expect it to work and is derived below. As you can see, we can simply factor out the I, j, and k values. Multiplication is a bit more complicated. When we have q times q prime, it requires us to distribute the components. If we use the modern definitions of the dot product and cross product, we can simplify the equation to what it is shown below, where q times q prime equals w times w prime minus v dot v prime, comma, v cross v prime plus w times v prime plus w prime times v. Notice that the multiplication is not commutative because I, j, and k do not commute. So that means the order of operations matter.
Next is conjugation. This is useful for other operations. To find the conjugate of q, we take the negative of the vector component of q. Next, we have inverse. This operation is how we divide quaternions. We see that q inverse is equal to the conjugate of q divided by the square of the magnitude of q. Notice that for unit quaternions, the inverse is equal to the conjugate. Next is rotations. The derivation for this is quite long, so it will only be summarized here. We see that p prime is equal to q times p on the left side, multiplied by q inverse on the right side, where p is w comma v, p prime is w comma v prime, and q is w1 v1. This is where quaternions outperform vectors. Computations of rotations only requires addition, subtraction, and multiplication. Other methods require use of more complex operations, such as sines and cosines, to perform rotations.
Okay, so what actually is a quaternion? If you're like me, then you aren't just satisfied with an algebraic explanation of them. You're hungry for an intuitive understanding. So what we aim to do here is give a better understanding of how four-dimensional numbers are used to represent three-dimensional points in space. Here, we will show how to visualize a unit quaternion in 3D space. We're only interested in unit quaternions because they are much easier to work with, but most of what's discussed here can be generalized to non-unit quaternions. We start with the basic quaternion equation with a scalar component w, an imaginary vector component r, where r is a unit vector. In the 3D view, the red arrow represents the vector r, and the blue arrow is the quaternion. For now, we will leave w at 0 in the quaternion, so that way we can build an understanding of how the imaginary component works. If we rotate r about one axis, then we start to notice that the quaternion seems to rotate double the amount r rotates. If we say that r is rotated an angle theta about the y-axis, then we see that the quaternion is rotated an angle theta away from r about the same axis. This makes the total rotation about the y-axis 2 theta for the quaternion. This is true for rotations about the x and y-axis. The factor of 2 in the rotations come from how quaternion rotation is performed. This equation shows how to rotate a quaternion P to a new location P prime. In order to do this rotation, we need to multiply by a rotation quaternion Q on the left side of P and the inverse of Q on the right side of P. The multiplication of Q 2 times is why the axis rotations are doubled. For the z-axis, something else occurs. The quaternion and r appear to rotate about the z-axis with the same angle theta. So what's going on here? Well, the quaternion is performing a second rotation, but it's along its local z-axis rather than the global z-axis. The second rotation becomes more apparent if we put a big wheel on top of the head of the quaternion. As we rotate about the z-axis, we see that the wheel appears to roll around. This is where the second rotation is going. Now that we have a better understanding of how the I, j, and k components affect the quaternion, we will start changing w to see how the quaternion changes. The w component can be thought of as a rotation about the vector r. We can rewrite the quaternion equation using an angle theta so that way this is made more apparent. Theta is the angle the quaternion rotates about the vector r. As you can see, if we start increasing w, then we see that the quaternion starts rotating about r. we will use an arrow that we can rotate to represent the angle theta. As we rotate the arrow, the quaternion acts the same way as it did whenever we were increasing W directly. Notice that the quaternion is rotated about r by 2 theta, just like how we saw for other axis rotations. As with most other aspects of quaternions, the rotation about r has some quirks. This circle shows how W rotations are changed when changing the imaginary component. We see that the circle appears to change radius, and its center point seems to slide up and down the vector r. The changes in the rotation circle are shown in these two equations, where capital R is the radius of the circle and C is the location of the circle's center point. To wrap it all up, we will now show various combinations of theta and r to show how a quaternion would generally rotate. We hope that you are now able to better visualize quaternion motion in 3D space.
Peter Guthrie Tait, 1831 to 1901. Tait was a mathematician born in 1831 in Dalkeith, Scotland. He lived with his uncle, where he was encouraged to make astronomical observations. He was enrolled in Edinburgh Academy, where he met and became friends with James Clerk Maxwell. Tait enrolled in Peterhouse, Cambridge, where he eventually graduated in 1852. During his early years, Tait was interested in a variety of topics within math and physics. In particular, he worked on a collaborative work, the Treatise on Natural Philosophy, which was received well. Tait read a copy of Hamilton's lectures on quaternions in 1853 and had a lot of correspondence with Hamilton until he was as familiar with quaternions as Hamilton. After Hamilton's death in 1865, Tait had to carry the torch of quaternions. Quaternions in Maxwell's equations. James Clerk Maxwell, 1831 to 1879, was a physicist born in 1831 in Edinburgh, Scotland. He is well known for his work on electricity and magnetism. In particular, his 1865 paper, A Dynamical Theory of the Electromagnetic Field, was very influential in developing electromagnetism. In 1873, he summarized his work in a treatise on electricity and magnetism. In the treatise, Maxwell made use of quaternions when writing his equations due to pressure from his friend Tait. Oliver Heaviside, 1850 to 1925. Heaviside was a physicist, electrical engineer, and mathematician born in 1850 in Camden Town, London. He left school at 16 due to illness and educated himself in physics and mathematics through independent study. He began his career as a telegraph operator, where he developed practical engineering insights that later guided his theoretical work. In the 1870s, he published papers simplifying and reformulating Maxwell's equations, introducing modern vector notation and the concept of impedance. Despite lacking a formal academic position, he was elected a Fellow of the Royal Society in 1891. In the 1880s, Heaviside introduced operational calculus and predicted the existence of the ionosphere, later named the Heaviside layer. He was known for his rejection of the quaternion approach and preferred vectors to express electromagnetic theory with clarity and precision.
Vectors before Heaviside. Before this point, the concept of vectors evolved gradually over centuries. In ancient Greece, ideas resembling vectors appeared in descriptions of motion and geometry, though they lacked formal notation. In the 1600s and 1700s, Isaac Newton expanded these ideas through his laws of motion, using quantities like velocity, acceleration, and force, each having both magnitude and direction, but still without a standardized mathematical framework. It wasn't until 1843 that Sir William Rowan Hamilton introduced quaternions, a four-dimensional number system combining scalar and vector parts. Quaternions gave the first formal representation of 3D vectors and rotations, but their complexity made them difficult to work with. Though powerful, quaternions weren't widely adopted outside of niche applications, until Heaviside simplified the vector component and redefined how we use them today. Heaviside's heavy step. In the 1800s, there was a growing divide in the math and physics community. On one side were supporters of Hamilton's quaternion system, which was a powerful but complex way of representing vectors and scalars in 4D. On the other side were engineers and scientists who needed a simplified and practical application to real-world problems. This is where Heaviside stepped in. Heaviside became annoyed with quaternions while studying Maxwell's treatise. He found them to be unnatural, so he modified them so that he could represent point using 3 components instead of 4. He rejected the scalar part of quaternions and focused entirely on the vector components, streamlining the map for practical use. He introduced the modern vector notation still used today and applied it to reformulate Maxwell's equations, transforming them from abstract theory into a form that could be widely used in physics and engineering.
Gibbs and Heaviside killed quaternions. Josiah Willard Gibbs, 1839 to 1903, was a physicist born in 1839 in Connecticut. He is known for his work in statistical mechanics. At the same time Heaviside was modifying Maxwell's equations, Gibbs was also developing a way to simplify quaternions down to vectors of 3 components. Heaviside started working with Gibbs to develop vector analysis. Their work culminated in a 1901 textbook, Vector Analysis, written by Edwin Bidwell Wilson, who was an advisee of Gibbs. This book was based on Gibbs's lectures and normalized vector notation to its modern form. This was the final blow to quaternions due to how much easier it was to work with vectors. Vectors had won the war. The aftermath. After the dust settled, quaternions started being used in the context of programming. Quaternions only require basic mathematical operations, such as addition and multiplication, in order to perform rotations. These operations are very computationally efficient. The main competitor of quaternions in the computational context is Euler angles. Euler angles require sines and cosines to perform rotations, and they have many issues that arise due to being more ambiguous than quaternions. And this is where we're left. Vectors are commonly used in physics, while quaternions are relinquished to special use cases.